Hello and welcome to the introductory lesson of the Apache Spark and Scala course offered by Simplilearn. This lesson will give you an overview of the course, its prerequisites, and the value it will offer you. After completing this course, you will be able to explain the process to install Spark, describe the features of Scala, discuss how to use RDD for creating applications in Spark, explain how to run SQL queries using SparkSQL, discuss the features of Spark streaming, explain the features of Spark ML programming, and describe the features of GraphX Programming. The Apache Spark and Scala training course offered by Simplilearn provides details on the fundamentals of real-time analytics and need of distributed computing platform. It will also explain Scala and its features. Further, it will enhance your knowledge on the architecture of Apache Spark. The course will also explain the process of installation and running applications using Apache Spark. Further, it will enhance your knowledge on performing SQL, streaming, and batch processing. Finally, it will explain machine learning and graph analytics on the Hadoop data. The course is aimed at professionals aspiring for a career in growing and demanding fields of real-time big data analytics. Analytics professionals, research professionals, IT developers, testers, data analysts, data scientists, BI and reporting professionals, and project managers are the key beneficiaries of this course. Other aspirants and students who wish to gain a thorough understanding of Apache Spark can also benefit from this course. Fundamental knowledge of any programming language is a prerequisite for the course. Participants are expected to have basic understanding of any database, SQL, and query language for databases. Working knowledge of Linux or Unix-based systems is an added advantage for this course, although it is not mandatory. Let's understand the value of Apache Spark and Scala to the professionals with the help of this case study of Oyala, which is a video services company that's based in San Francisco. It offers services to various media organizations including ESPN, Bloomberg, Yahoo, Japan, and Telegraph Media Group. It offers actionable analytics that allows them analyzing the manner in which their video content is being consumed in great detail. It's also enabling them optimizing their delivery standards for maximizing their revenues. The analytics engine processes of the organization achieve more than 2 billion analytics events every day. These analytics are obtained from about 200 million viewers across the world watching videos on an Oyala-powered player. Now, the challenge for Oyala was to deliver intelligence in real time by mining the stored data. The data included personalized content recommendations to clients and viewing patterns. In addition, the organization needed to run real-time interactive SQL query and MapReduce faster. This issue has been resolved by using Spark. Oyala can now perform real-time analytics using it. It has made Oyala a leading organization of big data technology. The organization now has the power to expand rapidly and offer real-time intelligence that are based on huge datasets. There are 7 core lessons in this course, apart from the current lesson, Course Overview. Take a look at the course map displayed on the screen. In addition to the lessons, there are some demos provided in the course to facilitate a better understanding of the concepts. This concludes the course overview. The next lesson is Introduction to Spark. All the best. Hello and welcome to Lesson 1 of the Apache Spark and Scala course offered by Simplilearn. This lesson will explain the need, features, and benefits of Spark. It will also compare Spark with the traditional Hadoop ecosystem. After completing this lesson, you'll be able to describe the limitations of MapReduce in Hadoop, compare batch versus real-time analytics, describe the application of stream processing and in-memory processing, explain the features and benefits of Spark, explain how to install Spark as a standalone user, and compare Spark versus Hadoop ecosystem. We need a new generation of distributed systems. Let's understand why. Nowadays, it's very rare that an organization exists that depends on its centralized computing. Irrespective of the fact, there are still many organizations that keep a tight hold on their internal data center and avoid any absolutely required data distribution. This sometimes happens because of their heavy investments in the infrastructure. Data centralization isn't prevalent nowadays because of various reasons. One of those reasons is a variety of client devices. The number and variety of these devices is increasing each year, leading to a complex array of endpoints to be served. Another reason is social, mobile, and embedded technology, as the amount and variety of the collected data is increasing exponentially. Also, landscape transformation and latency reduction is causing data centralization to decrease. With a few exceptions like high-frequency trading, or HFT, in which physically locating servers in a single location can lower latency, leveraging the distributed computing technology with parallel processing techniques transform the landscape and reduce latency. MapReduce used in Hadoop is not suitable for many reasons, such as it's not a good choice when it comes to real-time processing. It's batch-oriented, because of which it's executed as periodic jobs that take time to process the data and provide results. It takes minutes to complete a job, which mainly depends on the data amount and number of nodes in the cluster. MapReduce is also not suitable for writing trivial operations such as filter and joins. To write such operations, you might need to rewrite the jobs using the MapReduce framework, which becomes complex because of the key value pattern. This pattern is required to be followed in reducer and mapper codes. In addition, MapReduce doesn't work well with large data on a network. It works on the data locality principle and hence works well on the node where the data actually resides. However, it's not a good option when you need to process a lot of data requiring shuffling over the network. The reason is that it'll take a lot of time to copy the data, which may cause bandwidth issues. MapReduce is also unsuitable with OLTP that includes a large number of short transactions. Since it works on the batch-oriented framework, it lacks latency of seconds or subseconds. Another limitation exists with NameNode that tracks the metadata of about 600 bytes per file as estimated by Yahoo. This means that in the case of too many files, there can be a problem with NameNode. Additionally, MapReduce is unfit for processing graphs. Graphs represent the structure to explore relationships between various points, for example, finding common friends in social media like Facebook. Hadoop has Apache Giraffe library for such cases. However, on top of MapReduce, it adds to complexity. Another important limitation is its unsuitability for iterative execution of programs. Some use cases, like k-means, need such execution where data needs to be processed again and again for refining results. MapReduce, being a stateless execution, runs from the start every time. The features listed on the screen show a comparison of batch and real-time processing in case of the enterprise use cases. In case of batch processing, a large amount of data or transactions is processed in a single run over a time period. The associated jobs generally run entirely without any manual intervention. Additionally, the entire data is pre-selected and fed using command line parameters and scripts. In typical cases, it's used to execute multiple operations, handle heavy data load, reporting, and offline data workflow. An example is to generate daily or hourly reports for the purpose of decision-making. On the other hand, real-time processing takes place upon data entry or command receipt instantaneously. It needs to execute on response time within stringent constraints. An example is fraud detection. Note that Hadoop has different subsystems like Pregal, Grif, S4, and Drill for different business use cases. It would be better to have just one processing framework to solve all these use cases. Stream processing fits well for applications showing three characteristics. Let's first talk about computer intensity, which is defined as the number of arithmetic operations per global memory or input-output reference. Today, in various signal processing applications, this intensity is well above 50:1. Also, it's increasing with the complexity of algorithms. The next feature is data parallelism, that exists in a kernel when a function is applied to an input stream's records and multiple records can be processed simultaneously. This should happen without results waiting from the previous records. Data locality is the third feature that is a particular type of temporal locality and is general in media and signal processing applications, in which data is produced and read once or twice and then never again read. Intermediate streams can capture this locality directly. These are the streams that are passed between kernels and the data within kernel functions, and they do it using the model of stream processing programming. With column-centric databases coming, the similar information can be stored together, and hence data can be stored with more compression and efficiency. It also permitted to store large data amounts in the same space, which thereby reduced the memory amount required for performing a query and also increased the speed of processing. In an in-memory database, the entire information is loaded into memory, eliminating the need for indexes, aggregates, optimized databases, star schemas, and cubes. With the use of in-memory tools, compression algorithms can be implemented that thereby decrease the in-memory size even beyond what is required for hard disks. Users querying the data loaded into the memory is different from caching. This also helps to avoid performance bottlenecks and slow database access. Caching is a popular method for speeding up the performance of a query, where caches are subsets of very particular organized data that are defined already. With in-memory tools, the analysis of data can be flexible in size and can be accessed within seconds by concurrent users with an excellent analytics potential. This is possible as data lies completely in memory. In theoretical terms, this leads to data access improvement that is 10,000 to 1 million times faster as compared to a disk. In addition, it also reduces the performance tuning need by the IT folks and hence provides faster data access for end users. With in-memory processing, it's also possible to access visually rich dashboards and existing data sources. This ability is provided by several vendors. In turn, this allows end users and business analytics to create customized queries and reports without any need of extensive expertise or training. Apache Spark is an open-source cluster computing framework that was initially developed at UC Berkeley in the AMP lab. As compared to the disk-based two-stage MapReduce of Hadoop, Spark provides up to 100 times faster performance for a few applications with in-memory primitives. This makes it suitable for machine learning algorithms, as it allows programs to load data into the memory of a cluster and query the data constantly. As shown on the screen, a Spark project contains various components such as Spark Core and Resilient Distributed Datasets or RDDs, SparkSQL, Spark Streaming, Machine Learning Library or ML Library, and GraphX. The components of a Spark project are listed on the screen. The first component is Spark Core and RDDs, which is the foundation of the entire project. It provides basic input-output functionalities, distributed task dispatching, and scheduling. RDDs is the basic programming abstraction and is a collection of data that is partitioned across machines logically. These can be created by applying coarse-grained transformations on the existing RDDs or by referencing external datasets. The examples of these transformations are reduce, join, filter, and map. The abstraction of RDDs is exposed similarly as in-process and local collections through a language-integrated API in Python, Java, and Scala. As a result, the complexity of programming is simplified, as the manner in which applications change RDDs is similar to changing local data collections. SparkSQL is a component lying on the top of Spark Core. It introduces Schema RDD, which is a new data abstraction and supports semi-structured and structured data. This abstraction can be manipulated in Java, Scala, and Python by the SparkSQL-provided domain-specific language. In addition, SparkSQL supports SQL with ODBC JDBC server and command-line interfaces. The next component, Spark Streaming, leverages the fast scheduling capability of Spark Core for streaming analytics, ingests data in small batches, and performs RDD transformations on them. With this design, the same application code set that is written for batch analytics can be used on a single engine for streaming analytics. Machine Learning Library lies on the top of Spark and is a distributed machine learning framework. With its memory-based architecture, It's 9 times faster than the Apache Mahout's Hadoop disk-based version. In addition, the library performs even better than Val-Pal-Wabbit. In addition, it applies various common statistical and machine learning algorithms. The last component, GraphX, also lies on the top of Spark and is a distributed graph processing framework. For the computation of graphs, it provides an API and an optimized runtime for the Pregal abstraction. The API can also model this abstraction. As discussed, Spark was started at UC Berkeley AmpLab by Matej Zaharia in the year 2009. It was in 2010 when it was open-sourced under a BSD license. The project was then donated to the Apache Software Foundation, and the license was changed to Apache 2.0 in the year 2013. In the month of February 2014, Spark became an Apache top-level project. Then in November of the same year, it was used by the engineering team at Databricks to set a world record in large-scale sorting. Now Databricks provides commercial support, and they provide certification for it. At present, Spark exists as a next-generation real-time and batch processing framework. The graphic on the screen also displays the journey of Spark. We have already discussed that Spark provides performance, which in turn provides developers an experience that they won't forget easily. Spark is considered over MapReduce mainly for its performance advantages and versatility. Apart from this, another critical advantage is its development experience. Language flexibility is another important benefit that we will discuss here. Spark provides support to various development languages like Java, Scala, and Python, and will likely support R. In addition, it has the capability to define functions in line. With the temporary exception of Java, a common element in these languages is that they provide methods for expressing operations using lambda functions and closures. Using closures, you can use the application core logic to define the functions in line, which helps to create easy-to-comprehend code and preserve application flow. The components of Spark execution architecture are listed on the screen. It has Spark submit script that is used to launch applications on a Spark cluster. It can use all cluster managers supported by Spark using an even interface. Due to this, it's not required to configure your application for each one particularly. The next component is Spark applications. These applications run as sets of processes independently on a Spark cluster. These are coordinated by the Spark context object in the driver program, which is your main program. Spark context can connect to different cluster managers, which are 3 types: standalone, Apache Mesos, and Hadoop Yarn. A standalone cluster manager is a simple one that makes setting up a cluster easy. Apache Mesos is a general cluster manager that is also capable of running service applications and MapReduce. On the other hand, Hadoop Yarn is the resource manager in Hadoop 2. The last component, EC2 launch scripts, makes launching a standalone cluster easy on Amazon EC2. The interaction of these components is shown in the diagram displayed on the screen. Let's now talk about the next feature of Spark, automatic parallelization of complex flows. It's your task to make the sequence of MapReduce jobs parallel in case of a complex pipeline. Here, a scheduler tool like Apache Uzi is generally required for constructing this sequence carefully. Using Spark, the series of individual tasks is expressed in terms of a single program flow. To give a whole picture of the execution graph to the system, this flow is lazily evaluated. Using this approach, the core scheduler can map the dependencies lying between various application stages correctly. This allows parallelizing the operator's flow automatically without any intervention. With this capability, you can also achieve a few optimizations to the engine with less burden. An example of such a job is given on the screen. The screen also shows how this parallelization works through the given diagram. An important point about this structure is that every application has its own executor processes, which run tasks in various threads and stay till the duration of the entire application. While it benefits in terms of scheduling and executor sides by separating applications, it also implies that without writing to an external storage system, you cannot share data across applications of Spark. Another feature is the agnostic behavior of Spark to the cluster manager underlying. Till Spark can obtain executor processes and these can connect, it's comparatively relaxed to run it even on a cluster manager supporting other applications such as Yarn and Mesos. Note that the driver program needs to listen and accept connections coming from its executors all the time. In other words, the driver program must be accessible to the network to be addressed by the worker nodes. The driver schedules the task on the cluster. Therefore, it should run in proximity to the worker nodes, if possible on the same local network. To send remote requests to the cluster, you should open an RPC to the driver and let it submit operations from neighborhood. This is better than running a driver far through the worker nodes. As a developer, when you work with MapReduce, you generally get forced to combine basic operations to make them customer mapper reducer jobs. This happens because there is no built-in feature that could streamline this process. Therefore, some developers turn to the higher-level APIs for writing their MapReduce jobs. These APIs are provided by frameworks such as Cascading and Apache Crunch. On the other hand, Spark provides a powerful and ever-growing operators library. These APIs contain functions for the operators listed on the screen. These are just a few examples. There are above 80 operators available in Spark. While a few of them provide you operations that are equivalent to MapReduce operations, the others are high-level and allow you to write much more precisely. Note that when scripting frameworks such as Apache Pig, many high-level operators are also available. Spark lets you access them in the full programming language context. As a result, you can use functions, classes, and control statements as in a typical environment of programming. When it comes to speed, Spark has extended the MapReduce model to support computations like stream processing and interactive queries. The feature of speed is critical to process large datasets, as this implies the difference of waiting for hours or minutes and exploring the data interactively. Spark supports running computations in memory. Also, the related system is more effective as compared to MapReduce when it comes to running complex applications on a disk. These features add to the speed capability of Spark. Spark covers various workloads that used to require different distributed systems such as streaming, iterative algorithms, and batch applications. As these workloads are supported on the same engine, combining different processing types is easy. It's normally required in production data analysis pipelines. The combination feature also allows easy management of separate tools. Spark is capable of creating distributed datasets from any file that is stored in the Hadoop Distributed File System, or HDFS, or any other supported storage systems. You should note that Spark doesn't need Hadoop. It just supports the storage systems that implement the APIs of Hadoop. It supports sequence files, Parquet, Avro, text files, and all other input-output formats of Hadoop. Now the question is why unification matters. Unification not only provides developers the ease of learning only one platform, but also allows users to take their apps everywhere. The graphic shows the apps and systems that can be combined in Spark. A Spark project includes various closely integrated components for distributing, scheduling, and monitoring applications with many computational tasks across a computing cluster or various worker machines. The Spark's core engine is general purpose and fast. As a result, it empowers various higher-level components that are specialized for different workloads like machine learning or SQL. These components can interoperate closely. Another important benefit is that it integrates tightly, allowing to create applications that easily combine different processing models. For example, ability to write an application using machine learning to categorize data in real time as it is ingested from sources of streaming. Additionally, it allows analysts to query the data thus resulted through SQL. Moreover, data scientists and engineers can access the same data through the Python shell for ad hoc analysis and in standalone batch applications. For all this, the IT team needs to maintain just one system. The different deployment modes of Spark are explained on the screen. The standalone mode is a simple one that can be launched manually by using launch scripts or starting a master and workers. This mode is usually used for development and testing. Spark can also be run on hardware clusters that are managed by Mesos. Running Spark in this mode has advantages like scalable partitioning among different Spark instances and dynamic partitioning between Spark and other frameworks. Running Spark on Yarn has all parallel processing and all benefits of the Hadoop cluster. By running Spark on EC2, you have key value pair benefits of Amazon. The configuration options that can be passed to the master and worker are listed in the given table on the screen. This demo will show the steps to install Apache Spark on a Linux machine. In this demo, you'll learn to install Apache Spark on a Linux machine. As the first step, download the latest Spark tar file. Once the Spark binary is downloaded, move the TGZ file to the home directory. Now untar it by executing the given command. Now, you need to add the Spark installation path in the BAS-HRC file so that you can run Spark from anywhere in Linux. Add the given lines in the BAS-HRC file by executing the given command. Note that your BAS-HRC file location might be different based on your username and profile. Now let's reload the environment variable by executing the given command. Type echo spark home to verify whether the Spark home environment variable has been correctly defined or not. Go to the sbin directory of the Spark installed directory and type the given command to start master and worker daemons process. The steps listed on the screen depict how Spark applications run on a cluster. These applications run independently as different processes sets on a cluster. The Spark context object that lies in your main program coordinates the process. For running on a cluster, this object can connect to different types of cluster managers. We have already discussed different types of cluster managers. This allocates resources across applications. Once the system is connected, Spark acquires executors on nodes in the cluster. Executors are the processes that store data for applications and run computations. Then it sends the application code to executors. At the end, Spark context sends tasks for executors to run. One of the tasks that is performed on a Spark cluster is submitting applications of any type to a cluster. This is done using the Spark submit script. Another task is monitoring. Every driver program has a web-based UI that usually lies on port 4040. It shows information about the storage usage, executors, and running tasks. To access the same, go to the given URL. You can also schedule jobs on a cluster as Spark provides control over resource allocation both across and within applications. Companies like NTT Data, Yahoo, Groupon, NASA, Nokia, and more are using Spark for creating applications for different use cases. These use cases are stream processing of network machine data, performing big data analytics for subscriber personalization, and profile in the telecommunications domain, and executing the Big Content Platform, which is a B2B content asset management service that provides an aggregated and searchable source of public domain media, live news feeds, and archives of content. A few more use cases are building data intelligence and e-commerce solutions in the retail industry and analyzing and visualizing patterns in large-scale recordings of brain activities. The Hadoop ecosystem allows storing large files on various machines. It uses MapReduce for batch analytics that is easy as it is distributed in nature. In Hadoop, third-party support is also available. For example, by using ETL Talend tools, various batch-oriented workflows can be designed. In addition, it supports Pig or Hive queries that non-Java developers can use and prepare batch workflows using SQL scripts. On the other hand, Apache supports both real-time and batch processing. You can perform every type of data processing using Spark that you execute in Hadoop. For batch processing, Spark Batch can be used over Hadoop MapReduce. For structured data analysis, SparkSQL can be used using SQL. For machine learning analysis, Machine Learning Library can be used for clustering, recommendation, and classification. For interactive SQL analysis, SparkSQL can be used over Stringer, Tez, and Impala. In addition, for real-time streaming data analysis, Spark Streaming can be used over specialized library like Storm. A summary of this comparison is also given in the table shown on the screen. Let's summarize the topics covered in this lesson. Data centralization is becoming less popular because of various reasons, such as variety of client devices. MapReduce in Hadoop has many limitations, such as it's unsuitable for real-time processing. Apache Spark is an open-source cluster computing framework. The components of a Spark project are Spark Core and RDDs, SparkSQL, Spark Streaming, MLlib, and GraphX. Spark is popular for its performance benefits over MapReduce. Another important benefit is language flexibility. The components of the Spark execution architecture are Spark Submit Script, Spark Applications, Spark Context, Cluster Managers, and EC2 launch scripts. The different advantages of Spark are speed, combination, unification, and Hadoop support. The different deployment modes of Spark are standalone, on Mesos, on Yarn, and on EC2. Companies like NTT Data, Yahoo, Groupon, NASA, Nokia, and more are using Spark for creating applications for different use cases. You can perform every type of data processing using Spark that you execute in Hadoop. With this, we come to the end of the Lesson 1, Introduction to Spark of the Apache Spark and Scala course. The next lesson is Introduction to Programming in Scala. Hello and welcome to Lesson 2 of the Apache Spark and Scala course offered by Simplilearn. This lesson will explain the basic concepts of programming in Scala. After completing this lesson, you'll be able to explain the features of Scala, list the basic data types and literals used in Scala, list the operators and methods used in Scala, and discuss a few concepts of Scala. Scala is a modern and multi-paradigm programming language. It's been designed for expressing general programming patterns in an elegant, precise, and type-safe way. One of the prime features is that it integrates the features of both object-oriented and functional languages smoothly. It's a pure object-oriented language, as every value in it is an object. The object's behavior and types are explained through traits and classes. It's also a functional language, as every function in it is a value. By providing a lightweight syntax to define anonymous functions, it provides support for higher-order functions. In addition, the language also allows functions to be nested and provides support for currying. It also has features like case classes and pattern matching model algebraic type support. In addition, Scala is statically typed, being empowered with an expressive type system. The system enforces the use of abstractions in a coherent and safe way. To be particular, this system supports various features like annotations, classes, views, polymorphic methods, compound types, explicitly typed self-references, and upper and lower type bounds. When it comes to developing domain-specific applications, it generally needs domain-specific language extensions. Scala, being extensible, provides an exceptional combination of language mechanisms. Due to this, it becomes easy to add new language constructs as libraries. Scala supports the same data type as Java does, with the same precision and memory footprint. The table on the screen lists and explains all the basic data types used in Scala. These are byte, short, integer, long, float, double, character, string, unit, null, boolean, any reference, and nothing. The rules used by Scala for literals are easy and intuitive. Let's first discuss the integer and floating type literals. Integer literals are of integer, long, short, and byte types. They are available in two forms, decimal and hexadecimal. An example is given on the screen. On the other hand, floating point literals contain decimal digits. They may optionally have a decimal point and may optionally be followed by an e and an exponent. A few examples for defining such literals are given on the screen. Other types of literals are character literals and string literals. Character literals contain any Unicode character between single quotes. They are special character literal escape sequences. An example is given on the screen. On the contrary, string literals contain characters surrounded by double quotes. A few examples to define these literals are given on the screen. Another type of literals is the Boolean type that has literals true and false. A few examples for defining these literals are given on the screen. One more type is symbol literals, which are written with idents. An ident can be any alphanumeric identifier. An example of it is given on the screen. An operator is a symbol that conveys to the compiler that it needs to perform specific logical or mathematical manipulations. Actually, these operators provide a nice syntax for general method calls. For instance, consider the example given on the screen. In this example, the class integer includes a method called plus that takes an integer and provides an integer as a result. To invoke the plus method, you need to add two integers, as depicted on the screen. This demo will show the steps to declare and use basic literals and the arithmetic operator in Scala. Let's first learn how to use basic literals in Scala. Here we are going to declare and use literals such as long, float, character, and string. For this, we'll use the print-in statement. We will declare the long variable. Based on the value of the variable, Scala automatically detects the data type. To define the float variable, you need to use the character f at the end of the variable value. Doing so will let Scala make this variable as float, otherwise it will be treated as a long variable. If a variable's value contains only one character, then Scala treats that variable as the char data type. If a variable's value contains more than one character, then Scala treats that variable as the string data type. Let's see how to print a string in the console. If a string contains double quotes, then we need to use double quotes as an escape character. Now let's understand how to declare and use the Boolean literal and use different types of arithmetic operators in Scala. Scala automatically detects a Boolean data type if the value is either true or false. Let's now look at the use of logical operators like addition, multiplication, division, and subtraction. Scala automatically selects the data type for the result. if you specifically want to specify a data type as the long data type, you need to use the L character. This demo will show the steps to declare and use the logical operator in Scala. In this demo, you'll learn how to use the logical operator in Scala. Here, we're going to use different logical operators such as equal, greater than, and less than in Scala. You can perform the bitwise operation in Scala using the ampersand character. To perform an equality check, you can use the double equal to character. You can also use other logical operators, such as greater than, equal to, less than, and less than equal to. Many logical operators can be combined together in a statement, too. Scala provides a built-in mechanism called type inference, using which you can omit certain type annotations. Therefore, for example, it's generally not required to specify the variable type, as the compiler can deduce it from the initialization expression of the variable. In addition, you can also omit return types of methods, as they correspond to the body type and can be inferred by the compiler. An example to define type inference is given on the screen. For recursive methods, the compiler can't infer a result type. The program example shown on the screen will fail the compiler for the same reason. When polymorphic methods are called or generic classes are instantiated, it's not required to specify type parameters. The reason is that the compiler of Scala will infer these missing type parameters from the actual method or constructor parameters and the context. The example given on the screen illustrates the same concept. In this program, the last two lines are equivalent to the code given on the screen, where all inferred types have been made explicit. In some scenarios, using type inference can become dangerous. For example, consider the program given on the screen. This program does not compile, as the type inferred for variable object is null. Because the only value of that type is null, you can't make this variable refer to another value. To understand the concepts of a mutable and immutable collection, let's compare them through the table given on the screen. Mutable implies that it's possible to modify the collection in concern. Therefore, to change a collection A and every other reference to that collection, you can append elements using the given operator. On the other hand, immutable implies that the given collection object never changes. You would need to build new collection objects using the given operators. This helps in concurrent algorithms because it doesn't need locking to add anything to a collection. However, this feature can prove to be very useful. It may come at the cost of some overhead. As compared to mutable collections, immutable collections are fully persistent data structures. The difference between these collections is very similar to what exists between variable and value. A mutable collection that is bound to a value can be altered. However, you cannot reassign the value. On the other hand, an immutable collection cannot be altered. However, if it is assigned to a variable, that variable can be assigned to a collection built from it using operations like plus. In Scala, a function is a first-class value. Therefore, like other values, these can be returned as a result or passed as a parameter. An example to define such functions is given on the screen. Note that higher-order functions are the ones that take other functions as parameters or return them as results. An anonymous function is an alternative of named function definitions for small argument functions that tend to get created by parameterization by functions. It's an expression that evaluates to a function. These are defined without giving them any name. An example of such a function is given on the screen. An object is a named instance with members like methods and fields. In Scala, an object and its class have the same name. For instance, in this example, the first line has the keyword object, which is being used to declare a new object. It's being followed by the name of the object. In the second line, a value x is being assigned to the object instance. Note that the members of objects are similar to those of classes. Let's now discuss some of the uses of objects. One of the primary uses is to contain methods and fields that are independent from any environment. An example is math. This has the object name in the standard library containing multiple fields and methods depending only on arguments, if any, provided to them. Objects are also used to create instances of classes. An example is given on the screen. Note that in Scala, there are singleton objects instead of static members, which is a class with only one instance and can be created using the keyword object. In this way, Scala is more object-oriented than Java. Scala does not include built-in rational numbers. However, you can define them using a class. A class acts like a blueprint of objects. Once a class is defined, objects can be created from this blueprint using the keyword new. For instance, in this example, two variables, x and y, and a method are being defined. The method isn't returning any value. The variables of a class are called fields of the class, and methods are termed as class methods. The name of the class acts as a class constructor that can take multiple parameters. This demo will show the steps to define and use type inference, functions, anonymous function, and class in Scala. In this demo, you'll learn how to define and use type inference, functions, anonymous function, and class. First, we'll learn how Scala can infer the type of variable based on the type of operations and data. Now let's see how to define a function in Scala. Here, the function name is SumIntegers, which takes an integer parameter and returns an integer value. In Scala, small argument functions can be used as anonymous functions. Let's see how. Now let's see how to define a class and implement some methods inside it. Classes in Scala are static templates that can be instantiated into many objects at runtime. Here, we are declaring a class which takes two integer variables as parameters and has a method called addition, which will increment those two integers by 1 and print them in the console. Before you understand traits, let's first discuss the reason of its origin. In languages like Python and C++, you don't require interface as they have multiple inheritance, which is subject to the diamond issue. What will happen if you define a class inheriting two methods with the same type signature from two different classes? An interface is basically a set of properties and methods that an implementing class needs to have. For avoiding the issues of multiple inheritance, the Java designers instead decided to have single inheritance with interfaces to make the system a little flexible. Scala exists halfway between full multiple inheritance and Java's single inheritance with interface model, as it has traits. Traits allow you to recreate interfaces as Java does, and also lets you go further. Using traits, you can recreate the interfaces and implementation model of Java. Consider the given example to create traits in Scala. The code below shows how you can implement the student trait. Scala includes a rich set of collection library, which are containers of things. These can be sequenced as linear sets of items. They may be one element bound to 0 or have an arbitrary number. They can be lazy or strict too. Lazy collections contain elements that may not require memory until accessed, for example, ranges. In addition, collections can be mutable or immutable. Immutable collections can contain mutable items. You should note that mutable and immutable collections work better in different problems. In doubt, you should start with an immutable collection and change it later if required. The most commonly used collections type is lists. List X is a linked list of type X. An example is given on the screen. Another type is sets, which is a collection of pairwise various elements of the same type. An example is displayed. Scala maps represent a collection of key or value pairs. Consider the given example. Scala tuples can hold objects with different types like an array or a list. An example of the same is given. In Scala options, option X gives a container for 1 or 0 element of a given type. Consider the given example. The most direct method to diagnose all the elements that are returned by an iterator is by using a while loop, as explained through the given example. All operations on lists can be expressed using the given methods. Head is a method that returns the first element of a list. The tail method returns a list with all elements except the first. The third method is empty, returns true if the list is empty, otherwise false. The example given on the screen shows the use of these methods. When this code is compiled and executed, it gives the output shown. This demo will show the steps to use different operations on the list data structure. In this demo, you'll learn how to use different types of data structures such as list, set, map, tuple, option, and object in Scala. To define a list, use the list keyword and pass elements as parameters. Similarly, you can use set and map. See the syntax used for defining a map. A Scala tuple combines a fixed number of items together so that they can be passed around as a whole. Unlike an array or a list, A tuple can hold objects with different types, but they are also immutable. Here's an example of a tuple holding an integer and a string. An option is a container for 0 or 1 element of a given type. An option can be either sum, t, or none object, which represents a missing value. Let's create an object test that will have a main method to print characters A to D. As discussed, maps represent a collection of key or value pairs. You can retrieve any value based on the Scala map key. These keys are unique, however, values need not be unique. Also called hash tables, maps are of two types, the immutable and the mutable. Scala uses the immutable maps by default. If you need to use the mutable maps, you'll need to import scala.collection.mutable.map class explicitly. To use both types of maps in the same map, you can continue referring to the immutable map as map, but you can refer to the mutable set as mutable.map. The example given on the screen shows how to declare immutable maps. Pattern matching is supported by Scala for processing messages. This feature allows you to match on any sort of data using first match policy. This built-in mechanism is the second most widely used feature in Scala, after closures and function values. The example given on the screen depicts how to match against an integer value. The case statements block declares a function mapping integers to strings. The keyword match gives an easy way to apply a function to an object. A method containing implicit parameters are applicable to arguments like normal methods. This is because the implicit label has no impact. If the method misses arguments for its implicit parameters, those are provided automatically. The actual arguments can be of two types. First, these are all identifiers y that are accessible at the method call point without any prefix and denoting an implicit definition or parameter. And second, these are all members of companion modules belonging to the implicit type of parameters, labeled implicit. In the example given on the screen, a method sum has been defined that is computing the sum of a list of elements through unit and add operations. Note that the implicit value cannot exist at the top. They need to be members of a template. The stream class executes lazy lists in which elements are evaluated only when required. An example is given on the screen. Note that in Scala, a stream is a list with its tail as a lazy value. A value remains computed and is reused. In other words, the values are cached. This demo will show the steps to use different types of data structures in Scala. In this demo, you'll learn how to perform different operations on the list data structure by using head, tail, and isEmpty methods. Here is a class for immutable linked lists representing ordered collections of elements of type. This class comes with two implementing case classes, Scala nil and Scala double colons, that implement the abstract members isEmpty, head, and tail. This class is optimal for last in, first out, or LIFO, stack-like access patterns. If you need another access pattern, for example, random access or FIFO, consider using a collection more suited to this than a list. Let's summarize the topics covered in this lesson. Scala is a modern and multi-paradigm programming language, supporting the same data types as Java does. The basic literals used in Scala are integer, floating type, character, string, boolean, and symbol. Scala provides various operators like arithmetic, relational and logical, bitwise, and object equality. Type inference is a mechanism that allows to omit certain annotations and return types of methods. A function is a first-class value. A class is a blueprint of objects. Scala has traits that allow to recreate interfaces and implementation model of Java. Collections are containers of things. You can retrieve any value based on the Scala map key, which is unique but not its values. Pattern matching allows to process messages. A method containing implicit parameters are applicable like normal methods. The stream class executes lazy lists in which elements are evaluated only when required. With this, we come to the end of Lesson 2, Introduction to Programming in Scala of the Apache Spark and Scala course.